Dear participants, dear colleagues, we are starting now. Benoit Mandelbrot is a man of many parts. In particular, he is very effective in bringing an appreciation to the general public and young people. Must we be reminded that at the beginning of 1970s, he defined and named fractals, which described a multitude of objects found in nature whose indented forms appeared at smaller and smaller scales of observation to have similar shapes. Professor Mandelbrot called this phenomenon self-similarity. Thus, this new theory, popularized in the book The Fractal Geometry of Nature, fulfilled the dreams of a number of mathematicians who were working to the best of their ability to bring mathematics to the general public. Indeed, in one way, the mathematics were subtle and gave birth to new, deep theoretical problems. But in another way, they allowed a number of immediate examples to be understood and visualized. Clouds, topography of large towns, turbulence, etc. And finally, one can show fractals in color thanks to computer-generated simulation, and they are beautiful. I would like you to promise to visit, if you have not already done so, the exhibition Fractal Art, Beauty and Mathematics, which is in the Congress Center and also in the Condé Duquet Museum. Also, I recommend to visit in the Condé Duquet Museum the exhibition Experiencing Mathematics, launching through UNESCO with the help of IMU and ICME. I would like also to mention that Benoit Mandelbrot has been the honorary president of the ICM 2006 Benoit Mandelbrot Fractal Art Contest, and that the winners of this contest are in the exhibition on fractal art in this building at third floor. This conference and the cultural exhibitions around mathematics reflect the engagement of our Spanish colleagues, the IMU, and more generally the worldwide community in bringing mathematical culture closer to the general public. Certainly, fractals have an important place there. Thank you, Professor Mandelbrot, for we have learned that it is necessary to break the mirror of appearances and that many complicated objects without apparent form are in fact very beautiful. They are fractals.
Thank you very much for this lovely introduction. I must indeed say that this exhibit, in which I had no part except to accept to be the chairman of it, is something quite extraordinary. Yesterday we walked by the other place in town where it is being shown, and there was a long queue of people going to see a mathematical exhibit. It's rather unusual, to put it mildly. The fact that this exhibit is not purely mathematical is also very important, because it combines the mathematics with its very strong structure and the taste, the genius of many artists. Well, for me it has been an extraordinarily fulfilling situation to witness this phenomenon. And what I would like today is, first of all, to thank the committee for inviting me for this lecture, and then to present to you some of the very many facets of fractals, so as to give you a feeling for the extraordinary variety they represent and also their unity. Now, to begin, here is an alternative title: The Rough and the Smooth. Now, let us think, it's very difficult, but let us think to time very long ago when primitive man or woman was looking at the world, surrounding world. How many simple, smooth shapes does one see? Very few. One sees the moon, the iris, and the pupil of the eye. One sees, when a stone is thrown in a lake, the circles that create. Well, maybe a few more. 5 examples, 10 examples. Well, it's not important. Very few examples. Everything else was very rough. The trees, the clouds, the roads, the bark of the trees, everything was very irregular. Now, how did humanity react to this division between rough and the smooth? Anybody who writes a story knows that the story does not have much bite unless there is a fight between good and evil, or between one or another force of nature. In this case, it's not a fight, it's a coexistence between the rough and the smooth. Because the smooth was taken very seriously in every culture, developed, and then became geometry, then became mathematics, then became science. But the basic fact is that everything was smooth except for perhaps a few corners. So what happened to the rough? Was the rough neglected? Of course not. So I'm going to argue very shortly that the rough has been a very strong inspiration to many artists from time immemorial. When sometimes people ask me who has invented fractals, who has discovered fractals, my first reaction is, it's not me. In fact, it's nobody in the last 100 years or 200 years. It's somebody very, very long ago who first made drawings in which nature was simplified in either the Euclidean way or the fractal way. And so the definition of fractals, I will come to it very shortly. Now, I have this subtitle here, Fractals, Pure Mathematics, etc. Let me take these points one after the other. Now, in pure mathematics, fractals had a very important role around 1900. They were called monsters. But that's besides the point. They were not viewed as being in themselves of particular interest. And when I came up in 1970 or so, with a systematic study of them, people asked me, well, how many interesting things for us mathematicians are you bringing? Well, I know how to wait. It's one of my virtues. And I say, wait. Now, it's quite extraordinary that 3 of the Fields medals in recent years have been given to people who proved some conjectures of mine. One is the conjecture of the 4/3 for Brownian motion, which Wendelin Werner proved with Odin Schramm and Lawler. And another one is a conjecture about the equivalence of 2 definitions of the Mandelbrot set, which has been called MLC, and Yochoz and McMullen were rewarded in large part for this work. So in pure mathematics, this return of the eye, the return of picture, the return of the introduction of a re-establishment, rather, of the old relation between the hand, the eye, and the mind has been very fruitful. Not in proving anything, because a picture never proves anything, but to giving new ideas. And I will develop that a little bit later. Natural sciences, well, you'll see very shortly what's about. It's examples of very simple nature, of very crude nature, of very immediate nature. And then culture, Well, culture, in a sense, that culture just is a word for everything that man has created, whether it's great music or great painting or the stock market. These are not laws of nature. These are phenomena which man has created but does not quite understand. And so I will try to show you how the fractals enter in this context. And last but not least, in fact, perhaps foremost, the fact that humans of every kind, of every age, as a matter of fact, are attracted by fractals. It's not because I'm such a brilliant educator. I'm not. I'm completely unskilled. I started being interested in education very late in my life, when students came to me and said how beautiful fractals are and how much they make them want to learn about mathematics. So there was a hidden door somewhere, the door that in a way humanity prefers the rough to the smooth. And to finish my summary, that is not very surprising, because if you think again of primitive man, the world in which the man has evolved has been the world in which roughness was the rule. Smoothness was an exception of particular simplicity and loveliness, but still an exception. Now, let's look at this picture. It's very boring. Very, very boring. It's just a piece of land. And it's a geologist friend of mine who took this picture. Now, he told me something very important, that in his school, the professors always tell the students, if you go in the field and take pictures, always put an element of scale, so you would know how big it is. For example, put a camera cap, or put yourself. Well, so look at that and look at it again. Well, it's the same picture. It was cheating. It was not a camera cap. It was in fact a hula loop with a piece of a garbage bag on it. So what was for geologists a matter of police by the professor who tells the students always put an element of scale, can be turned around. Not as a question of order, do it right, but a question, why is it right? Why is it that if you forget to put an element of scale here, you can get completely mistaken and confuse a little pile of rocks with a big mountain? So this is kind of, folklore, which I made very big use of, because it turns out that almost every field has some kind of folklore of this sort somewhere. And when this is the case, the system is the same at all scales, and that is what I call fractal. Now, so the first observation is that scale invariance is common in nature. In nature and in culture, I may add immediately, this had been long known, but nobody could measure it, and could not be taken account of. So now we come to something else, which is one of the big turning points of every science. Basically, the sciences arose out of our sensations, because otherwise, how do we know the world? We know the world not by intuition, but by just touching it or being hit by it. So the world, we see light, we see sound, we see hotness, we see roughness. But think of it. Light and sound have been mastered long ago, around 1800. And so the color is measured by a frequency. And the pitch is measured by a frequency. That's very simple. Temperature is measured by temperature. Hotness, I mean. And but what about roughness? There was no measurement of roughness until very few years ago. It's very, very strange. All that was being done was to take those complicated landscapes that you saw and imagine that really they were flat, with a little bit of disagreement between flatness and the real shape. And in a way, one was applying the wrong tools for it. And, well, in these pictures, which I show very rapidly, to the left is one of the very first examples of measurement of property of rough surfaces. In this case, fractures of metals. And here is some very recent work, not so very recent, but much more recent, in which the data cover a very large range, 5 or 6 or 7 orders of magnitude, which in any science is very, very big. And so indeed, this idea that surfaces are very irregular, but the irregularity is the same at all scales, has proven to be a key idea. And the study of roughness is based upon that. Now, so a science of roughness, if exists, when it will exist, may be called rugometry. One must find many examples of it. I will not go into all these lines, but stop at the last one, because it's very important, so I don't want you to be tired when I get to it, and I have very little time to speak about it. When I introduced fractals into science and culture, namely stock market, my friends said, but why, how can you live in a rough world? Can we make use of it? And look around us. It may be that primitive man didn't see anything smooth, but today everything is smooth. This table is smooth. This room is flat. The marble in the lobby is so flat that I slide on it. It's very dangerous for me. Well, because the greatest source of smooth, regular shapes had been man himself, creating these engineering marvels. But today, people who are students of my students have no difficulty inventing devices to solve all problems and based upon roughness. Now, roughness was known forever in the vegetable world. Each of these pieces of cauliflower is like cauliflower. The lungs of man, for example, one has this exquisite structure in which if you take a piece of the lung, the structure of branching is very much the same. The lung has been now studied using fractals with exquisite precision. Two friends of mine, a physicist named Sapoval in Paris and an anatomist named Weibel in Bern, have gone well beyond what one could do before, because there is now a geometric basis for description of the lung, combining Weibel's old measurements and many other things which I brought and other people brought. And incidentally, here is, of course, another cast of a large dog. The reason is the dog and the man have the same kind of lung. But the way it is done is to put plastic, liquid plastic, in the air ducts of the lung, and then to heat it so it becomes solid. And depending how much you push, you fill in more and more of the space. Now, we had this model of a large dog's lung, I mean the real large, in our office. Michael Frame, myself at Yale, and one of our very distinguished colleagues walked by and said, "What is that?" Well, I said, "That is a space-filling surface. It's a piano monster." And here lies something very strange in terms of evolution of science. That when Peano, who was a very great Italian mathematician around 1890, defined a line that goes through every point of the plane, or a surface that goes through every point in space, this was treated as something bizarre, monstrous, as destroying something which you understand about nature. Well, that was due simply because they were not looking at real things. Because these kind of structures were known to everybody for a long time. This is a mountain, completely artificial, by my friend Richard Voss. And all that's included here, the main ingredient, more is self-similarity, more precisely self-affinity. It's a fine point. But by putting self-affinity and some conditions, very, very simple, one got out the relief like that. From viewpoint of understanding of the shape of mountains, it has been a very important step. Now, Galileo Galilei, who was the first scientist in a certain sense, wrote this marvelous text in which he speaks that the language of mathematics is necessary to understand nature. And he says, And its characters are triangles, circles, and other geometric figures without which it is humanly impossible to understand a single word of the great book of nature. Well, when Galileo said other geometric figures, it's quite obvious that he thought of other geometric figures in Euclid. But it's also very clear that the program which Galileo started stopped before reaching mountains. It could not describe mountains in a very simple fashion at all. And so what this picture represents is a total synthesis of a completely artificial landscape. It's reduced to one essence, which is this invariance. Now, in mathematics and physics, in most sciences that achieve a certain level of development, invariance is the key word. One tries to reduce the messiness of reality to a few things which don't change. Because everything changes, but some things, exceptions, do not. And these are the basic invariances. Now, question. Is every mountain fractal? Of course not. Is every sound represented by a sinusoid? Of course not. The sounds which can be represented by pure sine curves are the pure sounds which a skilled singer can sing. And they are exclusively vowels. Consonants are very complicated. So the same way as one speaks a pure sound, which is not my speech or even singing with consonants, one has now to speak of pure landscapes. Well, pure fractals. Well, the question is again, who invented fractals? The answer is impossible, because they have been absolutely there forever and forever, as far as humanity goes. Here is an example, a photograph of African village. The name of the village and the date are unknown because it is now a ruin. It was there before the colonization. Certainly it's very old, but if one looks at it carefully, which is difficult on this photograph, one finds that it was structured in a purely repetitive fashion. There was this oval, and then there was an oval for the chief's house, oval for his harem, oval for his chief minister. Everything was built upon ovals. But let's come closer, and closer also to Spain. In this scary picture, Dali has shown the horrors of war. And the main fact here is the repetitiveness, that in the eye and the mouth, there's a repetition of the same scheme as in the whole, and again repetition. Well, a man named Sierpiński was a very forceful person and a brilliant mathematician, created a kind of branch of mathematics which used to be called Polish mathematics. It had a very great influence on me directly and through an uncle of mine, but that's too long to tell here. But one of the structures he used very much in his work was this triangle, in which you take a triangle and take away middle quarters repeatedly. He doesn't say he invented it, and he's right not to say so, because if you go through Italy, you find that one of the two main patterns for pavement of churches at a certain period of history was precisely this one. So Italian masons knew it for a very long time. But let me come to the next picture. Before he drew this, he painted this painting, Dali sketched it the left. And you see, it was not repetitive. He found that this had less power, that this expressed in a too fussy, not enough direct form what he wanted. Therefore, without benefit of any mathematics in this context, he certainly put his construction in which he used fractals quite spontaneously. Now let's go back another century to this painter, who was a very great painter in Japan around 1800, one of the greatest painters in the history of humanity. He's well known for his great wave. But look at this picture. You have a mixture of very smooth shapes, Mount Fuji in the back. This is a picture which is part of a book called 100 Views of Mount Fuji, all of them drawn by pen. But if you look at the shapes on the beach, it's striking. They're exactly the kind of shapes that people who begin to work on fractals draw. As you go on, you replace every one of these intervals by a little generator, and you repeat. It's a very standard picture. Look at this one. Look at the shadow of a cloud on Mount Fuji. Well, it was very difficult for painters to draw clouds. It's very, very curious. The only painter who drew clouds with full force and effectiveness was Salomon van Ruysdael, a Dutch painter. In Holland, there is no mountains to paint, but there are plenty of clouds to paint. So van Ruysdael became very skilled. An Englishman named Constable did very well. But the main thing that many painters miss about a cloud is that the cloud is a billow. Then below, it has a kind of, well, you would call it a hierarchical structure. Well, Hokusai had it down pat. And you look at all the contours. You see also a house with some straight lines. So Hokusai was one of the great simplifiers of history of painting, in particular in this case there are colors involved, because he made everything geometric. Either Euclidean, the straight lines, and the Mount Fuji itself, or fractal. And that was long ago. Jackson Pollock. Last year it was a big furor because a physicist published an article in Nature analyzing this picture and showing that it was very, very close, has many strong invariances which were fractal. Shortly afterwards, somebody found a cache of 10 paintings which perhaps were by Pollock or perhaps not. And one of the criteria to decide they were not Pollock's was that fractally they are so different. Gustave Eiffel wrote a big book about his big tower. And he said that if I could have had a better steel, he would have gone further, because everything which looks like a beam in the Eiffel Tower is in fact a truss, that is smaller beams together. And he says if steel had been better quality and if rivets were stronger, he would go further. Malevich and so on. Well, I'm going to skip to show some pictures of this sort, but not discuss them. The question is, how do you define how do you measure roughness? How did I measure the roughness of these surfaces like I showed before these diagrams? Well, these measurements have a very interesting story. Around 1870, two German mathematicians, Lipschitz and Hölder, independently introduced a way of expressing the roughness of certain functions. These functions had no reality. In fact, they were supposed to be completely out of the world, not purely inventions of human mind. But to measure them, the usual things like tangent or other derivatives did not work, and so Hölder introduced this exponent. It had been modified and simplified, generalized in many ways. It is very powerful. And then Hausdorff introduced notion dimension, which he thought was just a matter of mathematical refinement for describing the very fine points of certain mathematical constructs. But turns out that one or the other of these expressions very often is the proper way of measuring roughness, and they are linked to each other. And then there is something other which comes in as you begin to, in a way, float freely and accept that nature is very complicated, that roughness is very subtle, that roughness reveals all kinds of complications. You find that it is necessary to introduce a concept which sounds like just science fiction, which is that of negative dimension. One replaces the notion of an empty set by a notion of latent set, which can have different dimensions. Of course, I have no time to say more, but it's a topic now of great interest. Now let me come to a topic which is very much at the order of the day at this meeting, since Wendelin Werner received the Fields Medal. Around 1980, when I was preparing the book that the President mentioned, The Fractal Geometry of Nature, I had the very strong feeling that nobody had looked at Brownian motion for a very long time. around 1900 or 1920, people did draw simple pieces of Brownian motion, the best they could. And then, every so often, you saw a picture, but it's quite clear that the pictures were there purely to decorate and not to understand. By then, I was a skilled observer of complicated shapes, and so I had my assistant draw a very big Brownian motion, and to make it more beautiful, I had it end where it started. It is a loop. Why so? Because if you start Brownian motion here and it goes, and here, the different points of the motion are different. It lacks homogeneity, therefore it lacks constancy. It's too complicated. And if you look for new things in a mess, you try not to look at everything at the same time. So I looked at that. Well, it was messy, all right, and not much clearer. But then it occurred to me, that's how it is defined. It occurred to me that one could perhaps simplify by erasing all these lines inside. So this shape here is one in which the plane is black, but all the trajectories which go from very far away until they hit this island whiten it. So the black is the inside and the white is all the points accessible from infinity. When I saw this picture, instantly I remembered islands which we have generated in our work on geomorphology. I'm always very familiar with them. So familiar that I could give dimension very accurately. I would say this curve is dimension a little bit less than 1.5 or a little bit a bit more than 1.7, because dimension is a true measurement of roughness. That true in a sense that conforms to our hand and our eye. If temperature, for example, had been completely unrelated to the ordinary feeling of hotness, it would not have been a good number. But temperature confirms what good cooks know about hotness. And here the fractal dimension confirms what a skilled eye knows. Looking at that, I had instant reaction. Dimension is 4/3 of the boundary. It was a conjecture. It was reported in my book, which has been mentioned. It triggered great mathematical activity. Bertrand Duplantier almost proved it. In a sense, he proved it completely, but by physical argument. And then Lawler, Schramm, and Werner proved it correctly. And Werner has received this medal. He's the youngest in the group. This has been a very difficult problem. First, the people thought it was just something for a weekend, for tomorrow, for a weekend, for a week, a month, a year, a century. Finally, it took 18 years. The computer rendering can be creative. That is, if you modify an object and if you make your mind and your hand and so all together, it increases their power enormously. Well, let me continue and mention in this book. The very fact that so many young people came towards me shortly after this book came out was totally astonishing, because nobody expected anything new from this fractal geometry. But in fact, they have come in large numbers. In the bottom, you see a simulation of relief. It's completely fake. On top, you see this Brownian snowflake, Brown Island. But the interest that young people manifest for it is very, very strong. As I mentioned, I don't think it's because of my charismatic personality in the least. It's because humanity has been trained in a world of great roughness, great complication, and is more comfortable with complication than it is with simplicity. Mathematics is different in that it seeks simplicity, and the notions that something is simple mathematically, that should be easy for the child, it was an old belief, but it does not seem to be true. Well, other shapes in physics do the same. There is an interesting quote by Cantor, Georg Cantor, the creator of set theory, which says that mathematics the art of asking questions is more fruitful than the art of solving them. Well, I hope there is some truth to that, because in my case, I did not prove much that was difficult, but I certainly asked many questions of my friends. This is a very simple shape which is completely ununderstood. After enormous efforts, it's more or less stuck. And then we get to this marvelous shape, which it was my good fortune to look at very carefully and make observations about. These observations include many which have been proven well, one in 6 months, one in 5 years, one in 10 years, but the main one is still open. That is, there are two ways of defining this object. I thought they're identical, but knowing my limitations as a technician, I did not spend more than 20 minutes trying to prove it. And this has been going now for 26 years, and two people came close to proving it, again, Yokoz and McMullen, but they're still open. It was modified to be called Mandelbrot set is locally connected. Well, that's what Herbert says about this set. I would like to show you a few of the pictures on which I discovered the properties of this set. So these are images which came out. To make them reproducible on this slide, I had to take my original pictures and Xerox them repeatedly. Because it was not the bright, colorful pictures that you all know, but it was slightly dark gray on rather light and dirty gray on a machine called Versatech, which no longer exists. And the question was precisely to see what was dirt and what was reality. I was helped by a rather ridiculous incident. Let me come back to this thing. The first picture of this set that we did, I was in such a hurry to have it for reasons I could explain, but that are irrelevant, that I did not tell my programmer to do only the top part. Of course, by looking at the definition and so on, it is symmetric. But so he did the whole thing, and it was mess of the worst kind. Points all over the place, and little black blotches. But then there are two separate islands, exactly symmetric on top and bottom. And mess, noise, machine imperfections do not create symmetric blotches. So I realized that these things were real and interesting and worth looking at, and obtained this picture here to the right. Well, these are other pictures, again, in which we evaluated that. And then here are some pictures which were before. The difference was that when I did these pictures here, I was at IBM. Have been at IBM for a long time by then, and I had a very good assistant, very good machinery, and we could make nice pictures. The previous picture I showed you were done at Harvard under very hostile conditions because the system was very, very imperfect. Now, this was too complicated. I was looking at these pictures, and we did many pictures like that. Now I understand exactly what they are. But when I saw them first in 1979, there was too much there. And in a certain sense, what I was trying to do, was complete madness. Imagine the following stupidity. You want to study organic chemistry, or chemistry in general, but instead of starting with simplest molecule, which is the hydrogen or water or something, you start with, well, not a very complicated one, not DNA, but ethyl alcohol or something of the sort. It's too complicated. You get to there after you learned about water, for example. And so these pictures, I was trying too much and didn't see anything. Incidentally, there's something called lattice chaos, which older Frenchmen know about. My uncle was very enamored of it, so I learned from my uncle at a young age. And I had, you see this picture in 1979 on top, this little thing, that was a Mandelbrot set, but I did not know it. The environment was too complicated. It's by simplifying that I saw the interesting observations. Well, let me proceed. Well, this is having fun. everybody knows by now that you can have fun. Let me get to the final topic I would like to discuss, and it's a matter of the variation of financial prices. It is not a recent interest of mine. In fact, it's a very old interest of mine. I have the first time that I did work which created a big sensation in a field was in the early 60s when I analyzed financial prices of various kinds. But I returned to it, and in the early 60s I was simply fighting excessive odds. At that time, the community of economists and finance theorists had suddenly remembered or realized that in 1900, a very interesting character in Paris named Louis Bachelier had written a PhD dissertation called Theory of Speculation. And in that dissertation, he introduced a process which turned out to be identical to Brown motion and coming before, and he postulated that prices follow Brown motion. Now, if prices followed Brown motion, the world would be very, very simple. You could say that if prices follow Brown motion, the extraordinary cost of establishing prices would have been very much simplified. But prices do not follow Brown motion. And so here's the example which shows this fact very strongly, and I would like to tell you a little bit about my way and the way of some people of navigating between very pure mathematics and very, very much hands in on the task. To the right, the lower lines, the 5 lines from bottom, they represent either actual prices or imaginary prices, simulations of prices according to a model which I introduced. Now, most people cannot tell the difference, because both the real prices and the imaginary prices of this category, the special kind of imaginary price, have the property that every so often there's a big price change. Mind you, these are financial prices, not prices paid in a grocery store or at retail, which are entirely different and much more complicated story. And it is not either the price of oil, which is very much influenced or determined by cartel, the OPEC. These are prices of commodities which are simplified, normalized, some kind of, for example, securities, stocks, bonds, or commodities, for example, American upland cotton, 15, 16, 7 inch, which is the quality of cotton, and that is very actively traded. Every so often, for a good reason or for no visible reason, these prices change instantly by enormous amounts. Now, one sees that very much if one follows a little bit, not very closely, the markets. For example, pharmaceutical companies in the US at this point are subjected, right or wrong, to very, very close supervision of everybody. And if a medication is very good for millions of people, but every 10 out of a million die, well, it's not acceptable any longer. So, some time ago, not so long ago, a big company had a pain reliever which unfortunately killed a number of people. When this became public, the price of the stock of that company went down by 1/3 instantly. Not rapidly, but instantly. It was a discontinuous function. When in some companies there is some very good new boss comes in, the price can go up double, because one trusts that a new director, a new president is going to make the company work better. Or if a very good director dies in a car or helicopter accident, the stock may go down because one expects him to be down. Then sometimes it goes up and down for no reason. But whatever the reason, or lack of reason, one must understand that the phenomenon we're studying is intrinsically and fundamentally discontinuous. and that the discontinuities are a very, the most directly tangible aspect of it. In an article which I wrote with a friend of mine who has been for many years a very active trader in New York, we wrote an article in which we compared an index, Standard & Poor, with what the index would have been if the 10 largest down price changes in the last 10 years had not existed. So the last 5 years, prices went down many, many times, and you just eliminate the 10 worst at every point in time. Well, the index under these conditions would have more than doubled. In other words, 10 events are as important as everything else. Now, I would like to stop a little bit the discussion of prices for something much more fundamental, which is getting used to the notion of set of measure zero. The idea of set of measure zero, many of you know it, you may not know it, but it's a very important notion which came up around 1900, in particular through the work of Lebesgue and Borel. And the principle is that in physics, you say if you have something which is true, except for a set of measure zero, you can neglect the except. You can say it is true, because the set of measure zero means that once in a blue moon, after a million years, you may be wrong, that's not important. In these things which I'm telling you about, the whole interesting stuff is effectively in sets of measure zero. Sets of measure zero can split into smaller and smaller ones. If that had been motivated by pure mathematics, it would have been viewed as a very interesting new line of pure mathematics. But it was actually motivated by very practical uses in the understanding of these phenomena. And so the question arises, given what the market is, what happens in the long run? Because the usual argument for statistics is to say, well, on the small run, short run, things go up and down all the time, but on the long run, everything averages out, and nothing interesting is left. This is, again, the basis of very fundamental theorems, the law of large numbers, the center limit theorem, and other such immensely important results. Well, they are theorems. And a theorem is true when the conditions are true. When the conditions are not satisfied, the theorem gives you a wrong result. So how would you make the experiment here to see whether the averaging out works? Well, instead of looking at these records to the right, which are perhaps a matter of 5 years, look at the 100 years to the left. Well, the 100 years, it's plotted a bit differently. I couldn't find the same plot. But it has been equally erratic. That is, prices do not average out very simply. Now, to finish this, looking at this diagram, look at the top line. The top line corresponds to the original Bachelier process, the Brownian motion, which is an extraordinarily interesting mathematical construct, which I admire greatly and use all the time, but which does not apply here. Because on the top line, there are just a little bit, some points where it goes a little bit faster than elsewhere. But basically, it is just all within a strip. And the bottom, there are many, many points going up, then they are clustered, many things occur. Well, let me continue and show you this thing very quickly. It's very important in all these cases when one navigates in the total unknown, because it was truly attention of everybody was so much concentrated on Brownian motion that this was not considered. So it was very important to make cartoons, simplified pictures, which are not true, but which have some elements of reality. And so here you just have a price which you interpolate recursively. Well, now you see cartoons. On top you see something which is almost the same as Brownian motion, only in bottom something which is worse than in stock market. Stock market is halfway. But by tuning a single parameter, in this case, one number makes you go from one to the other. Well, here's various ways of doing it, and I will not go into details. Here you can have discontinuities. Here you can have a strong dependence, positive or negative, all kinds of interesting things just by this argument. And here, something which is perhaps for specialists, for people who have a more pointed interest in it, which is, well, there is a quote of the late former President Ronald Reagan of the US, who said after visiting a forest of redwoods that you have seen one, you have seen them all. They're all the same. That is, if you look at pieces of brown motion or white noise, it's very difficult to tell the difference. But these 8 pieces are exactly the same in terms of structure. They look completely different. If you make the wrong analysis, you find that they're different. If you make the right analysis, you find they are the same. And so the key here is that fractals are not just a way of restating old things. They are certainly very powerful in this context. Well, there's phase, space. I will not go in that. These are experimental data. But the main point here is this one, and then I'll return to the beginning and to that exhibit. That roughness is a frontier that science long ignored, and now it must be faced. And it is not something which in a way improves our knowledge of optics or our knowledge of acoustics, but makes another human sensation, a very basic one, as basic as hotness, perhaps, accessible to investigation. And so here you have this very simple idea that roughness can be tamed, and then at the same time, as I showed you by some of the few pictures of art, and as you can see by picture of fractals, which are all over the place, in particular this wonderful exhibit, the same kind of thinking is of such extraordinary beauty. So there is some hope in sense of unity of knowledge, or more precisely, unity of knowing and of feeling. That for daily work, it is indispensable to go into details, and details of everyday life are completely different for a mathematician, a physicist, or people in other fields. They must do it according to the rules of the field. But behind these differences, there are some very basic similarities of structure. Now, I have taken a very complicated and rather dangerous path in my life. I did not become a member of a well-defined community. In a way, I can call myself a throwback, a kind of living organism which should have vanished long ago, who believed in solo science, the science one does by oneself, which means that in every field I've touched, I had to stop rather soon, because rather soon I became incompetent. I've done my contribution in the first few steps. And the fact that the themes of my life have been so completely different in one way and so completely identical in another is what I find so particularly striking. Now, this is the second time that I've been invited to present, to speak to this International Mathematical Congress. The first time was in 1983, immediately after my book, The Fractal Geometry of Nature, which you see here the cover of. It was translated to Spanish and Italian and many other languages, Russian, Japanese, Chinese, etc., etc. Now, at that time, all that was completely unknown and unexpected. The only thing, the big message which I had then was that the mathematics which I had learned in school as being the monsters invented by Peano, by Cantor, by Sierpinski, by the great men of around 1900, these monsters, in fact, were not monsters at all. They were just good descriptions of the structure, of the messiness of nature and of culture. It was not It was an early message. But as time went on, as more people took it up, it has proved to be a very strong one. Now let me go rapidly through some books. These two books, and these two are part of my selected papers. One of them is Mandelbrot set, one on finance, two others are on noises. This is a book which I published very recently, well, in English it was published a year and a half ago. In Spanish it just came out, and in which I was joined by Richard Hudson, who was then a prominent financial newspaperman who was retiring from that job. Wrote the book together, in which my views of variation of prices are explained, and also my views of science, and also my views of the relation of mathematics and of reality. You may have noticed that unless I made a very bad mistake, I did not use the following words. I never spoke of applied mathematics. I don't view myself as being an applied mathematician. As a matter of fact, almost nothing that I have done is classified as applied mathematics. I certainly have studied many mathematical structures. I give you a few examples. Many physical structures which required totally different mathematics to be mastered, and many structures in the living beings, vegetal and animal and stock market. I could have gone on elsewhere, but never did I go into applied mathematics. It's not a matter of judgment. It's a matter of, in a certain sense, perhaps example. I think that mathematicians, with their training, if they add sufficient amount of openness and interest, not only in development of mathematics, but in their relevance to problems, can be extraordinarily powerful. For example, a mathematician who comes to stock market and just asks a professor of finance what's interesting will get an answer completely different from if the person goes to a trader and asks a trader would be very interesting. These people are very different people. Some love my work and others don't like it. Now, finally, I understand that after my talk there will be some session of fractal music. And I would like to end on that for two reasons. One of them is somewhat personal. A great friend of mine named Ligeti, George Ligeti, died recently. Ligeti was, in my generation, I think the greatest composer in a classical mode. He had the first many periods in which he was showing off and writing music that was very irritating to many people, but he told himself that this was just a necessity, because in music, if you don't do something to get noticed, nobody knows you exist. But once he became noticed, he went back to basics of music, and when he died, he had not finished a series of suites for piano, which was hoping would be, I think, 24, and he wrote only 17 or 18. They are amazing. And Ligeti one day came to me and said that he, very famous composer, I knew him very well, I was listening to his music, that he never had understood his music until he saw my pictures and heard me talk. And how can I, who know nothing about music except that I'm very fond of music, I'm very familiar with music, how can I influence George Ligeti? Well, he told me the following. He was educated in Romania. He was Hungarian living in Romania, according to what was in effect the Paris Conservatoire of 1900. So all the basic things about orchestra instruments, he got a very solid training. But nobody would tell him in any formal fashion what distinguishes a real piece of music from just noise, noise, noise. He learned it by trial and error, very often by error. He would bring to his teacher, who was a very forceful and brilliant man, he brought to him a piece, a composition. The teacher looked at that, dreadful, too many notes, Not in the sense that the Emperor of Austria told Mozart there are too many notes, but in the sense that he was fussy. There were little details all the time, and the little details were overwhelming the great flow of music. So he went the other way, and he wrote another piece, and the teacher told him, there's not enough detail. You just go up and down, that's not enough. And then he understood by practice, by long and tedious practice, that you must have balance. That in every piece of music, there may be balance of, long, slowly moving themes or thing, and fast moving down to almost the size of a sound, which becomes, where music vanishes and acoustics takes over. Now, this learning, he told me, is exactly that music must be fractal. That there must be the same kind of structure in the detail as overall. That the detail and overall belong to the same piece. They are not separate from different words put together in one thing. They are the same. And that had been understood by musicians in every culture, again from time immemorial. One sees traditional songs from advanced civilizations or complicated civilizations, and recent songs from very isolated cultures. They all have this structure. And that structure is something which humanity has discovered all by itself, without the benefit of any mathematical or conceptual thing. But it makes a big difference when such a structure is discovered. Again, I did not discover it. Friends of mine discovered it. Ligeti, Warinen, another great composer, alive, and other friends who are just doing experiments for fun. But in all these cases, there's a very complicated, messy environment in which, if you try to describe everything in detail, you become an accountant and not a scientist. But mathematics, properly understood, can help reduce that to a very small number of very powerful ideas. And this idea of scale invariance and the corresponding mathematical tools, which become more and more numerous, are particularly important for that purpose. So I wish you a good visit to this exhibit, and thank you again for inviting me to present my ideas in this audience.